Okay, so in that case, you see, it's a 1D problem. Okay, it's up or down. So here, the thing to understand is that the largest force, okay, it's going to tell you which way is the acceleration. The acceleration will have the direction of the largest force. So in that case, the weight is larger than drag. So that means the acceleration will be down. Do you agree with that? So usually starting from now, we're going to take the positive direction in the same direction as the acceleration. So if you are accelerating down, we're going to take plus to be down. You're going to see why when we get to more complex problem, it's going to be easier to solve. And then I'm going to say the largest. So I call that the winner. Okay, so let's call it the winner. So winner minus the loser, which is the drag, equals mass times acceleration. Okay, so in that case, you also have the winner down, okay, but the acceleration will be smaller. But you have to understand that it's still speeding up, but not at the same rate. Okay, so it means the acceleration is decreasing. It's still gonna go faster, but not at the same rate. Okay, so it means if you look at the velocity versus time, okay, this is important because I'm connecting to math, right? So if you have velocity versus time, if you take the slope, you get the acceleration. So the acceleration, you see, it's going to decrease, but the speed is still increasing. So you see the slope is the acceleration. So here it has a large slope, it's going to be 10. The slope here at the beginning, because it's there is no air drag, and then it's going to decrease, and here you have acceleration equals to 0. So that means it has reached its terminal speed, but it doesn't mean that it stopped mid-air. Okay, it just means that the weight equals the drag. Okay, so it means it's in a dynamic equilibrium, which means the acceleration equals 0. That means the velocity stay constant. It's going to be the terminal speed, but it's still going down. You are still going down. Now, what's going to happen if you open the parachute? All of a sudden, you're going to increase the surface area. Okay, so the drag, the air resistance will increase significantly. So it means, which one is the largest now? Is it air resistance or is it the weight? Air resistance. So it means the acceleration will be up, but you are still going down.
That now is the positive.
So then you can take up to be positive. Okay, so in that case, you're going to slow down, but it doesn't mean that all of a sudden you're going to go up. You are just slowing down. Okay, and because you are slowing down, the drag is proportional to the speed square, and it depends on the shape here and depends on the surface area. But as you decrease your speed, the air resistance is going to decrease. Okay, and then what's going to happen? It will decrease until it's going to match with the weight. And in that case, you reach a new terminal speed, so you can hit the ground safely. And you're going to not break some bones. Right? So it's not that obvious to understand. Because I wanted to go back to this. That's from my other class, but I thought. Okay, and then for the pop quiz, you're going to have something like this. And I want to make sure you know how to do it because I went fast last time. We were talking about system. Okay, so you want to know exactly which system you are applying Newton's law to. Okay, so for example, if you have this system here, how can I move this? Okay, so you have this system here, and let's say what is given, let's say I give you, okay, this is 1 kilogram book, so 2 pounds, this is 4 pounds. It's a physics book, yeah, heavy book. And let's say you are pushing, let's say there is no friction, okay? So as long as you are pushing, there is an acceleration, and the acceleration is 0 meter per second per second. Listen, because that's going to be on the pop quiz. Hello, hello. Hi. Okay. So let's say you want to find, let's say the question is find the push here. So the first thing you want to do is to define the system. It could be those two books here. So you can imagine you put them, and it's going to be important for what coming next. Imagine this is an imaginary bag. So that will be your system with the two books inside. Okay, so the external force here is just your push. What's going on inside is none of your business. You don't want to look inside. They are killing each other. It's not your business. So if you want to find the force, the push from your hand, you're just going to say the push from your hand equals the mass will be the mass of your bag, which is 3 times 0.1. Is that clear? Now, if you want to find the force between the two books here, so then you have to change your system. Now you're going to place this book in that bag here. The hand is not touching it. The only thing touching that book is the other book. Right? So this book is pushing this one. So then you apply Newton's second law again. That will be the external force 1 to 2 equals the mass of your bag, which is 2 times the acceleration is the same, of course, and 0.1. Okay, so that will be 0.2 Newton. And then if you are asked what's going to be the force F21, it's going to be the same, because for every action you have an opposite and equal reaction. But it all depends what is it that you put inside your bag. Now, if you decide to put, and you will find always the same acceleration, right? You can decide to put this one in the bag. So if you put this one, you see it's being touched by two external force. It's being touched by the force from the hand, and then you have this one resisting, and then you have its mass, which is 1, and you have the acceleration, and you will get the same thing. Okay, so in physics or engineering, civil engineering, whatever, you have to define your system, and then you have to define the external forces, and whatever is inside, it's not your business. They kill each other out. Okay, so I wanted, because that there was one question about that. So that will be slide 59. Okay, we did that. Okay, so here it's easy to understand. So on Earth, so this is the Earth here, and it has a center, and this is you on Earth. Okay, it will be acted upon by a force which we call the pull due to gravity. Okay, inertia is the mass, so the weight will be equals to mg. G on Earth is about 10 meters per second, and it depends on the radius and the mass of the Earth. Okay, so G actually equals to a constant times the mass of the Earth times the radius square. So this is the mass of the Earth, that's the radius of the Earth, and if you plug into it, you're going to find about 9.8. Okay, that's a constant. It was found by Cavendish. Doing an experiment, it was found. And this is 6.67 times 10 to the negative 11 and some units here. Why negative 11? It means gravity is very, 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 very small, very weak. It's a very weak force. Look how strong I am. I can defy gravity. It's very easy to defy. It's not like the electric force. The electric force is very, very, very strong. Otherwise, we won't have any shape, right? The electric force is what keeps us together. All the molecules bound together. But gravity is very weak. Otherwise, you will not be able to walk on Earth. And so for gravity to really to be experienced, you need a very, very large mass and a big large mass here, and it depends on the ratio between the mass and the radius square. Is that clear? So by the way, the Earth, because the Earth is what's rotating, it has like kind of a shape like this, like a football. So the radius here will be larger at the equator. So this is the axis here. Going for the North Pole, the Earth is rotating 24 hours, takes for one cycle. So it's a little bit larger here at the equator. So that's why G will be a little bit smaller at the equator than on the North Pole. Okay, so we have less weight if we live in Miami than if we live in New York, right? You can say, oh, I lost weight. So if you go to the equator, you will lose even more weight. Okay, so you do the computation and you get 9.8. Okay, what else? So mass here, that's what we call inertia. Okay, so a weight of 1 kilogram on Earth will have a mass of 1 kilogram on Earth will have a weight of 10 Newton. So you can imagine that the Earth, okay, is grabbing the mass and pull it toward the center. So it's pulling here. So you have a spring. It's a spring scale, and you're gonna read 10 Newton. 10 Newton is the SI, the international system. So it's in Newton. But in British system, it's gonna be about 2 pounds. That we are the only one to use on Earth still. Not even the British, they don't use it anymore. We are still using it, and another country that I forgot about. So obviously, if you have 2 kilograms, that's going to be a pull of 20 Newton, which is about 4 pounds. Okay, so 10 Newton is about 2 pounds. Any question? It's good. So if you go to Mars, for example, G, the acceleration due to gravity, the mass is smaller, so it's going to be about 4. On Earth is 10. So inertia will be the same, but not the weight. So it's going to be easier to do to lift on Mars than it is on Earth. So if you go to the moon and your mass is 80 kilograms, on Earth, will the mass change on Earth? No, right? Inertia is the same. Only your weight will change. So if you go to space and you are far away from any gravitational field, the weight will be 0. But it doesn't mean that the mass will be 0 because the mass is the amount of stuff inside. If you go to the moon, your weight, so this is 1 kilogram. 1 kilogram will weight 1.6 Newton, which is 6 times less than on Earth. So gravity on the moon is divided by 6. So the weight is divided by 6, but the mass is the same. And if you weigh that 1 kilogram, which is about 2 pounds on Earth, the weight is about 10 Newton. Okay? So Here, for example, astronaut on Earth, 120 kilogram is the mass. It's going to be the same on the moon, but the weight will be divided by 6. Okay, if you are on an asteroid, I forgot what's the name. This is a famous asteroid because it looks like a potato and it has a tiny moon. Forgot the name. But if you were to stand on that asteroid, you have to be very, very careful because if you jump, you won't come back, right? Doesn't have enough pull. Okay, very quickly here. Okay, so what's the weight here? About 2.5 kilogram. The weight will be 25 Newton. Or you're right, about 5 pounds because you multiply by 2. Okay, if it's on the moon, the weight will be divided by 6. Okay, on Earth, so those are tricky questions because with the multiple choices with the test, okay, they try to confuse you between weight and mass. So if you see 340 Newton, don't confuse with the mass. The mass is 34 kilogram. So when you're going to use Newton's second law, the net force equals m times acceleration, you want to use the mass. But if in your equation you are using the weight, okay, it goes on that side of the equation. So don't confuse both. The mass of a dog here will be what? Yeah, very good. 7.5 kilogram. That will be inertia. And then 10 pounds. So 2 pound is about 2 pound is 1 kilogram. So 10 pound will be in mass, in the mass. In kilograms, it's gonna be 5 kilogram, right? More or less, or 10 Newton. So textbook 4.7, do remember to go over your textbook, especially if you're going into engineering. If you are preparing for the MCAT, you have to study as we go along. So this one, 4.7, that book is great because it has very nice solve problem. Okay, so you have a truck. And then what? Okay, it says 2.45 times 10 to the 4 Newton. Newton. So here is the weight. So right away, you have to convert that into mass. So you have to divide by 10. So that will be kilogram. Okay, usually you don't put that here. You just put the mass. You just want to have the mass here because that's going to give you inertia. Okay, so it's going to go this way. And then it says it's stopping. So if it's stopping, it means it's going to slow down. Do you agree? So that means there is a static friction because the wheel stops from spinning, and so it's going to slide and then it's going to stop. So you have static friction here. And the magnitude is 1.83 times 10 to the 4 Newton to the left. And they want you to find the acceleration. Bless you, bless you, bless you. Well, it says go back. So I go back. So F equals ma. So 1.83 times 10 to the 4 equals the mass times acceleration. So in that case, you have to, so it depends which one is plus, which one is minus. So for this one, when it's easy like this, I can take this way to be negative, but it's up to you. You can take it also to be positive. So the acceleration will be in this direction because the largest force is also in this direction. So it will be minus 118.3 equals 2.45 times acceleration. So the acceleration will be minus, okay, that's easy. So of course, in one of the multiple choices, they will take the case when you forgot to divide by 10 the weight to find the mass. Obviously, I will have like half, or maybe no, maybe not, maybe a third of the students will do that mistake. So make sure that when you use Newton's second law, the mass is the weight divided by 10. Okay? Okay, if you have any question, let me know. Let's move on. Okay, so we have the weight. Let's look at another force, which is not that intuitive, and it's called the normal force. So what does it mean, normal? It doesn't mean that you have abnormal force, cuckoo force and not cuckoo force, right? Normal is a mathematical term, and it means perpendicular. It means that force here will be always perpendicular to the surface. So each time a surface is touched, right? A surface is like made of little spring. It's like made of tiny springs. These are the molecules, right? The molecules, they behave like little spring. And when they're going to be squeezed, they're going to squeeze back. So that's going to be the normal force. And it's always perpendicular to the surface. Always perpendicular to the surface. Always, always. Okay? So if it's very simple like this, okay, that's no problem. It's easy. You have the earth cooling down. Okay, so you have the surface being squeezed. So it's going to push back, and that will be called the normal force. And you can see that here, if I have a normal force, see, it's like you imagine any surface to be squeezy, can be compressed. So you push on it, it's going to push back. So it's not that, so imagine this, right? Being squeezed, so it's going to squeeze back. If it's in equilibrium, like this one, you're going to have up equals down. So the weight here will be equals to the normal force. Okay, so here is the tricky thing. In physics, they always have those very challenging problems involving inclined plane. So if you have a mass on an inclined plane, the normal force is perpendicular to the surface. Students want to do the normal force up. No, 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 no. Normal means perpendicular. It has to be perpendicular. So you can imagine like the inclined plane is made of all those springs, right? So it's being pushed, it's going to push back. It has to be perpendicular because normal means perpendicular. Perpendicular. And then you have the weight. The weight has to be straight down to the center of the earth. Students want to do the weight this way. No, 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 no. The weight has to be toward the center of the earth. Okay? So each time you have an inclined plane problem, normal is perpendicular, the weight is toward the center of the earth. Okay? Now people think that you have a normal force only from the ground, but you also have from the wall. So let's take a look at this guy. So I just want to focus on him. Because here they put all the reaction force. I don't care about the reaction force. I just want to focus on him here. I'm gonna place him okay. I don't care about that. I don't care about the reaction force. I'm focusing on the person here. So I'm looking at the external force. He's pushing on the wall is pushing back. This is a normal force. Okay? It's a reaction force from the surface because he's squeezing the wall. And then you have the weight. The earth is grabbing, pulling toward it. And then you have the normal force from the ground. So you have two non-normal force and they are not equal to each other. You push the ground is pushing back. And also you have a static friction. That's if the guy is standing like this, no, I don't slide. If it was ice, I will slide. I don't slide. That's because there is static friction between my feet and the ground, right? So you have static friction here, and he's in equilibrium. We call that static equilibrium because left equals right, up equals down. Down. So down will be the weight, up is the normal force, left is the static friction, right is the normal force. If there's no static friction and you push on the wall, he will slide. Okay? So two things. You have to define your system, and also you need to have a normal force each time you have a surface. And normal means perpendicular.
I sent you the video.
Okay, thank you. I did like just now.
Like
Okay. Okay, there is this experiment you can do on action reaction. I don't think it's the same, but it's like if you want to show that the force is always the same, not the consequence. So you have two people, someone less mass, someone more mass, right? With a yoga ball, and they run toward each other. And of course, the one with less mass will bounce back because the acceleration is larger. So when you are bouncing back, there is a very large acceleration, and the one with a more mass, he will just slow down. And but it's not very. I have to do it where it's like soft because it can hurt. So usually they do that with a guy and a woman, right? The woman will bounce back and the guy hardly slow down. But the force is the same because the squeezing is the same. Okay, the yoga ball is being squeezed, right? So the force is the same, obviously not the consequence. I wanted to show you that, but then I might get in trouble, it's not safe. But it's a very nice application. So normal means what? Perpendicular, very good. Okay, so what do you think here? So this is a block, earth is pulling on it, but you are pushing also. So the floor is reacting to the squeezing. So what do you think the normal force is going to be? 26, you all agree with that? Imagine a normal force will be the reading on the bathroom scale. So imagine you have a huge bathroom scale that they use for cattle, for example, a huge bathroom scale. You're going to push on the bathroom scale, you're going to increase the weight. Okay, so the normal force is what we're going to see the apparent weight. Okay, the apparent weight will increase. And what do you think here? So the weight is still the same. So Earth is pulling, but you are lifting, but not so much that it's not touching. It's still touching, but it's being lifted. So what do you think? 4. Very good, right? Because the floor has sensors, so it's gonna feel less force. Okay, you can do that experiment if you want with a bathroom scale. Okay, so what do you think here? So if you have a bathroom scale on an inclined plane, and you see the force acting on it will be the weight and normal force. But do you think it will push on the surface as hard as if the floor is flat? So this is flat. You are on a bathroom scale here. So you're gonna have your weight down, and that will be the normal force, and the normal force will be the reading on the bathroom scale. Now you are standing here on the bathroom scale. Okay, so you still have the normal force, but the weight here is straight down. So the weight has two components, right? It has a component here that is trying to make you slide, but we don't care because you have some friction, but it has a Y component here. So are you pushing as hard on the floor? No. So your apparent weight will be less, decreasing, right? You can do the experiment also if you put your bathroom scale here and you are here. Of course, yeah, there will be no reading, right? Because you are not pushing. So the pushing back is a reaction force, and that will be called the apparent weight. So if you want to cheat, like if you are an athlete and they're bothering you because you need to lose some weight, so you take the bathroom scale and you put some like a pen underneath or a pencil or something that will make an incline, and all of a sudden, wow, look at that, I lost those pounds. So you can do that experiment here. See, I made an incline, and you see, I put something underneath. I don't know how to go back. It's supposed to be 150 and now it's 130. It's 150, blah, 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 and it's 130 instead of being 150. Okay, so you're not going to push as hard, so it's going to push back not as hard. So this is called the apparent weight. Your apparent weight is less. The apparent weight is always the normal. Okay, here is another example of apparent weight. If you are on those rides here, so it's a circular motion. In your frame of reference, you're gonna be pushed on the wall. The wall is gonna push back, and you're gonna feel very heavy depending on the speed. So if you were able to put a bathroom scale, a vertical bathroom scale, that will be called your apparent weight. Your apparent weight will increase enough that even if they remove the floor, okay, they can remove the floor, you're not going to slide. Or if they put the thing vertical, you are not going to fall, okay? Because the centrifugal force will be larger than your weight. Like that the experiment that you did. But you're gonna feel very heavy. So the apparent weight is how heavy you're gonna feel. That will be equals to the normal force. So if you are in a free fall, so if you are in a space station, for example, in orbit around the Earth, you are constantly falling toward the Earth, right? So your body, the bathroom scale, the the space station, they are all falling toward the Earth. They want to go in a straight line at a constant speed. No, you can't. So you feel weightless. It doesn't mean that gravity gave up on you. In the space station, it's about 96% of gravity up there, but it means that you don't feel your own weight anymore, right? You don't have any normal force to push back on you. So they call that weightlessness, but it doesn't mean that you are weightless. It just means that there is no normal force, right? The apparent weight is zero. So if someone is in an elevator and evil physics professor cut here the cables, right? You're gonna fall. The bathroom scale is gonna fall. All that will have an acceleration of g. You cannot push on anything, so you feel weightless. Okay, so this is called weightlessness. Okay, so that will be in an elevator your normal weight. If you are accelerating up, you're gonna feel heavier. Does it make sense? Okay, because it's like you have inertia, you want to stay here. The floor has to push you. Okay, so the weight here will be more. The normal force will be more. And if it's accelerating in the opposite direction, you feel less. Your stomach feel butterflies, right? And then that will be very bad. That will be zero weight. And they have that, like they have a special airplane that you can pay. I forgot what it's called. Zero gravity airplane. You can pay for it and you can experience weightlessness. So what they do, they zoom, accelerate up. So now you are on the floor. You cannot lift your body, okay, because it's pushing upward. At the top here, they cut the engine. But because it has momentum, it's going to do a projectile motion. It will keep moving along a straight line, but at the same time, it's falling. It's in free fall. Okay, so it's follow a parabola. So you're going to be in free fall inside and you're going to float. You can pay for that at the time when I made the video. So I don't know if you can still pay for it, but it looks very cool. Okay, this was a real, they did that advertisement a couple years ago. They did it in such a plane. So it's a very famous, I don't know how much it costed, but it's a real thing. Okay, it's not fake. It's not AI. They really did it a couple years ago. Um, and then you can do really cool things in free fall. So I don't know if you see, it's like Michael Jackson here. They have like they are hooked. Okay, so that's why they're not going to fly away. And they did some kind of experiment. So that will be free fall, weightlessness. And they did a classroom also with teachers.
Chance to go with Igor. The science teacher treated to the zero gravity experience, and I got to go too.
So when they take up, when they go up, they feel very heavy. So heavy, they cannot lift themselves, right? So that's cool. And I think it's called zero gravity airplane. I don't know, but I think you can. You have to pay for it, right? Okay. So if an elevator accelerates upward, um, what? Greater, very good, right? And okay, if you like physics and you want to go even more advanced, a little bit more advanced, you have amazing YouTube lectures. I mean, they were MIT lectures by Walter Lewin, and he does this experiment. I would dream to do it, but I can't. My knees cannot take it. I don't know how he will do it. Like he's very athletic. I don't know for his age. So he will jump here from the desk, and you see that the gallon that he has in his hand will float. So if you have good tendons and you are very flexible, and you can show that, you can do that experiment. I can't. And after that, he attached a bathroom scale under his feet, and he was able to show with something, to collect it, so with a pillow underneath, to show that the bathroom scale will go to zero. Okay. You need good knees. I don't have good knees. Okay. Okay, so another type of force is called the tension. So tension, we're going to suppose that the rope, so here you have a rope or a cord or a cable, is not flexible. It's not flexible and it's massless, because otherwise it makes things more complicated. So in that case, the force is transmitted, transfer. Okay? So for example, if 1118, I have to cut that, 1118. No, just a simple pulley here. If you are pulling with 10 pounds, you can lift 10 pounds. So the force here will be the weight. This is 10 pounds. Okay, so you have to balance out 10 pounds. So the force, this one and that one will be equal to each other. So the force will be the same. Okay, so the force is the same. So if you have a cable here, everything happens like this. Mass is acted upon just by the tension that you're applying. So the force is the same on both sides, only if it doesn't stretch and if it's massless. Okay, so the force is transmitted. Why would you want to do that, for example? Because then you can add your own weight to pull, so you increase the force, and it's just changing the direction. Okay, is that clear for the tension? We're going to have a lot of problems with tension and pulleys. And then spring force, easy to understand. Each time you have a spring, or like if you go to the gym, you have those Pilates band, right? Something that you can stretch, right? Or if you do the bench, for example, you also have those things to help you lift the weight. It's called a slingshot, right? So in that case, it's behaving like a spring that is being stretched or compressed. Then you're going to have what it's called a restoring force. Okay, that force wants to bring back the band or the spring to its initial length. It doesn't like to be compressed, it gets upset. So it's like a reaction force that wants to bring back the spring to its initial position. So this is called Hooke's law, named after Robert Hooke. the one that Newton hated. He didn't like Robert Hooke at all. Robert Hooke is the one who made the first microscope and was able to look for the first time at cells, in plants. But Newton didn't like him because he dare criticized him. So Newton got upset and he made fun of him. I told you the story, right? Because Hooke was very small. He had like a birth defect, so he was very small in size, like this. And Newton said the famous quote, "If I have seen so far, it's because I'm standing on the shoulders of giants." So it has two meanings. First meaning, I'm so smart, I use the work of Galileo, Kepler, and Copernicus, and I develop physics. Or it means I am a giant, and you are, nothing. So Newton was not a very nice guy. So anyway, this is called Hooke's law, and it says that the restoring force is proportional to the restoring force is proportional to the stretch, or the how much is being compressed. Okay, X. So I can show you that.
Wait, so we assume the spring is mass.
Hmm?
We assume the spring is mass. We assume
The spring is what?
we assume the spring doesn't have any mass.
Yes, we suppose that no, the spring can have mass because we are focusing on the load only. For some problem, yes, the spring will be massless. But in that case, for example, let's say, uh, I don't know which one is it. Okay, so if I take a 50 gram, so that will be your load. So that one will have a load, right? Even though the spring can have a mass in that case, doesn't matter. But sometimes, because we are focusing on the load, but some problem we will say a massless spring. You're right. Okay, so let's see. So the stretch is about that much, about 10. Do you agree? 10 centimeters. Do you agree? Right? So it's acted upon by two force, the weight pulling down, so that will be like a stress. And then there is a restoring force. And the restoring force you're going to see is proportional to the change in length. So if I multiply by 2, you see this is at 10, right? Do you agree? I'm going to multiply by 2 the mass. Multiply by 2 the mass. Here. Oh, do you see? It's multiplied by 2. So the amount by which the spring is stretching is proportional to the amount of force it's being pulled on, right? So F equals kx. If I multiply the mass by 3, so 150, it's very hard to get it right. Here, up, you see it's multiplied by 3. If you multiply by 4, of course, it's going to be multiplied by 4. Okay, it's going to be multiplied by 4 about. Okay, so this is called Hooke's law. And if you are in engineering, for example, you learn about strain and stress. So what we call the strain, right? So for example, here you are pulling like a spring, for example, or something that can be stretched out. The strain will be delta L over L. So the amount of deformation relative to its initial length. And what we call the stress will be the force applied per unit area. And they are proportional to each other. That's Hooke's law. It's just that in the case we're going to deal with, it's just a little bit more simplified. And you can have the same thing in 3D. Okay, so it means that the deformation delta L over L will be proportional to the force per unit area. Okay, so the stress is proportional to the area times delta L over L, and that's going to be called K. So F equals K delta L. So that's the general equation, and that will be what we're going to deal with. K depends on the type of spring, how stiff it is, and its area. Is that clear? Okay, so the real equation is actually F equals a constant that will depend on the spring, how stiff it is, and then that will be the area of a spring, the cross section. This is the area here. And then here you have the initial length. So that will be the initial length, and that will be delta L. Okay? Or you can say F over the area equals something like this, delta L. And delta L over L is called the strain, and this is called the stress. So it just means that the stress is proportional to the strain. Okay, you don't have to worry about that. Here we're just going to use that equation here, F equals Kx. X is the amount by which the spring is being squeezed or stretched out. K is called a spring constant, and it depends on the shape of a spring and how stiff it is. Okay, so that's how, if you do Pilates, for example, they have easy, very easy, super hard, medium. It will change that constant. The spring constant will change. Okay, higher, stiffer is the band, harder it is to stretch it. Okay, so then we go to a free body diagram. We already talked about that. Like you make a X, Y coordinate system. Your body will be at the origin, and you are looking at the forces acting on it. Okay. Okay, so we get to Newton law, how to apply Newton law. So you have to decompose forces into components and the acceleration also. So you have the net force equals ma along the x-axis and along the y-axis. Let me explain. Let's take an easy example here. So that will be Newton's second law. So you are using a vector equation. Okay, it's a vectorial notation. And then you decompose it along the x and along the y. Okay, so let's try to do this one. Let's try to find, and I'll show you how I do it for the student, but you don't have to do it my way. You can do it your way or the textbook way. So the goal is to find the acceleration. If there is an acceleration. So here, what you have here is the friction. It's a kinetic friction. If it's moving, it's kinetic friction. If it's not moving, it's static friction. And we're going to find out if it's static or kinetic. So first of all, do you expect to have an acceleration up and down? No, right? Nothing is happening up and down, which means up equals down. Up is killing down. Let's say you have an acceleration this way. Okay, so I'm going to take, because there is an acceleration this way, I'm going to take positive to the right. So that will be for the winner, that will be for the loser. And then I'm going along the x-axis. Okay, so first I'm going to do my free body diagram. So that will be your mass here, 20 kilo. Okay, so this force here, you see there's a pull. So this is a pull here. It's in the first quadrant. So attach the tail here. I'm going to place it here. Always attach the tail or the vector to the origin. That's going to be your 60 degrees. Agree? Exactly. Okay, and then you're going to have frictional force here, which is to the left. So that will be 15. Of course, you're going to have the weight straight down. Weight is pulling down, and you push on the ground, so the ground is pushing back on you. But we are focusing along the x-axis. So a force comes into components. Each component has a different job. Okay, so this is the push P. So P sub x will be how much of P is along the x. That's the driving force. That's the one that make the motion possible. And then you have a y component. So the y component is teaming up with the normal force. They go together to fight the weight. Okay, so they lift it a little bit, such as you're going to have less kinetic friction. But we are only interested in the x-axis. So we're going to say the winner minus the loser equals mass times acceleration. Or you can say right minus left equals mass times acceleration. If you do it this way, you only put the magnitude. So here, what is pulling to the right? It will be the x component, so 150 cosine 60 minus the loser here, 15 equals inertia 20 times the acceleration. Okay, once you understand that, everything else is going to be easy. Okay, you have to decompose the motion into two components. So the acceleration will be, so cosine 60 is 0.5, so 75 minus 15, 60, right, divided by 23. So it's accelerating. If I found zero, that means it's not moving. It means that, or maybe it was moving. It could be moving, but at constant speed, for example. If I find an acceleration of zero, could be at rest or it could be moving at a constant speed. Question? Okay, so this is a skier, and this is an inclined plane. Can you trace the forces? Can you do a free body diagram? Can you trace the forces on him first? And then I will ask you to buckle your seatbelt and to memorize first, and then memorize how to do this kind of problem, and then it will grow on you. I don't know how much is that. Maybe 40 degrees. And let's say he's accelerating down. Hmm? The third quadrant, 1, 2, 3. Yes, the weight will be in the third quadrant. So the first thing you want to do is to take the x-axis along the acceleration because it's going to make the job easier. So in all those inclined plane problems, you always take, I don't know how to make a straight line, you always take the x-axis here along the inclined plane, always. Since the x-axis is this way, so then you want to have the y-axis here perpendicular to it. Okay, you memorize that. And you take plus down, so that will be easier. Okay, so down will be plus. This is a plus. This is a plus. That will be a minus. And then there is no friction. So what will be the force acting? You have the weight. Do you agree? Okay. Always the weight this way because students want to do this. No, 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 no. The weight is toward Mother Earth. So this is Mother Earth here and it's grabbing, pulling toward it. Right? So always this way. And then students wants to do the normal force this way. And you say, no, 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 no. Normal is perpendicular. So the normal force has to be perpendicular. I'm trying hard. Perpendicular because you see it's pushing little spring here, it's pushing, it has to be perpendicular. So you have the normal force this way, the weight there. Then you have to memorize the following. You can do the math. I mean, it's geometry, but memorize that angle here or the incline will be always the same as this one. That angle here will be the same as this one. Always. You memorize it. You don't ask why. You memorize it. If you want to know its geometry, right? If you have a sector here and you have a perpendicular there and you have a perpendicular there, that angle will be the same. At home, you can think about it, but that angle has to be the same as this one. Do you agree? Y-axis. Y-axis. Always. You memorize it. This angle here will be always the same as this one. You memorize it. And then you make the component. So you go from the tail to the head. That will be your x component. Okay. How much of the weight is along the inclined plane? That component is what will make you go down. Slope. And this is the component here. The y component is busy pushing into the snow. So that component here will be equal to the normal force. But this one is the one that will provide the acceleration that will be diluted. That's why Galileo used inclined plane. You with me? And then you memorize that the x component of the weight is mg sine. Whatever angle you have here, and the weight component is mg cosine. I mean, if you're good, you can see that will be sine, but it's better to memorize because if you memorize, you don't have to lose time. You memorize it. You agree? And then along the x-axis, in that case, there is no friction, but you could have friction. But in that case, there is no friction. So it means the winner minus the loser, there is no loser, equals mass times acceleration. So the winner is mg sine 40 equals mass times acceleration. You with me? Okay, do you all agree? Right, I'm applying Newton's second law along the x-axis. And then you go bye-bye. So in that case, if there is no friction, You see, the acceleration is the acceleration due to gravity, but diluted. That was the genius of Galileo. That's how he was able to show the kinematic equation, because he diluted gravity. How much is sine 90? 1. So if there is no slope, if it's vertical, acceleration will be gravity, right? So you are diluting gravity. Okay? And along the y-axis, you see that mg cosine equals the normal force. So that will be your apparent weight. That will be your normal force. So if you take a bathroom scale here and you weight yourself, I don't know how you will do that when you ski, but like if you had enough friction, you push on the snow, you will see your apparent weight. Right. I don't know. Like the bathroom scale will have to go with it. Oh, I don't know. Okay, any question? So you memorized it.
Yes.
Yeah.
Explain again why it's
Why is sine?
going down.
So going down, so you have the x component here, right? So which is the same as this one. So if you take that right angle triangle, okay, it does something like this. So this is 40 degrees, and this is mg, and that's your x component, right? That will be your x component over mg, right? But you memorized it. Okay, the x component of the weight is always mg sine. Okay, and that will be cosine. Agree? Okay, so if you do the geometry here, if you were to do the geometry and you add those two vectors, let's say you do a parallelogram vector here, parallelogram approach here, you add those two vectors together, or you do tail to head, you see that the net force, that will be the net force, right? So I did before with components, but you can do it with vectors, right? So the net force is the vector sum of the normal force plus the weight. So you see that the net force will be along your slope here. And the net force will be equals the mass times acceleration. So acceleration is just the net force per unit mass. So your acceleration will be here. Okay, and because you're inside your net force, you're gonna have the mass. It's gonna cancel out, so it doesn't matter how heavy it is. It's gonna go down at the same rate if there is no friction. Because it's in free fall, it's like an elephant or a dog, going down slope. If there is no friction, they both go at the same rate. Because it's in free fall, like the hammer and the feather, except gravity is diluted. Okay? That because the net force depends on the mass. Okay, so then, okay. So here the weight has two components. Sometimes it's called the parallel component. This one is the perpendicular component. This is mg sine, and that will be mg cosine. Agree? Let's see what happens if you have friction now. Yeah, let's see if you have kinetic friction now. So do the drawing with the skier, but now you have kinetic friction, and you have the mass, and you have the angle. Can you find the acceleration? Okay, same thing, but now I have a mass, 50 kilogram. The angle is 40 degrees, and you have the kinetic friction. Usually it snow. That's why they want to make the ski very with wax, right? So you can go faster. Otherwise, you still have friction. Okay, do. I don't know. Should I take this one? So that will be your weight. Or maybe I take the little guy. Okay, do it. 50 kilogram. So 50 kilogram, right? Mm. So you memorize X, you go down slope, okay? X-axis always along the slope, always. Okay, and what else do you memorize? You know that the weight is straight down. Okay, normal force is perpendicular. Okay, you have your X and Y axis. So this is X and this is Y. You memorize. That's going to be 40 degrees. And now you have friction. So friction is always opposing the motion. Do you agree? And this is 120 what? 121 Newton. The magnitude of the weight is 500 Newton because the mass is 50 kilogram. So you memorize that the X component of the weight is mg sine. You memorize it. And this is mg cosine. So along the x-axis, we're going to say the winner minus the loser equals mass times acceleration. So mg sine 40 minus the loser 121 equals 50 times the acceleration, right? So mg is the weight, but it's diluted a bit. So mg sine 40 minus 121 inertia 50 times a. Mm. So what is cancelling out? What? It doesn't work? Wow, 321. Yeah, no, but I have friction now. So, yeah. So you are right. You are right. If there is no friction, so A equals G sine. But now you have friction, so the mass matters. Because more mass, you are pushing more on the snow, you increase the friction. Harder you push, more friction you get. Yes. So minus 121, 121, enter, you divide by 50, you get 4. Okay. Oh, you can divide 50 on both sides. That's what you said? Yeah, you have to be very careful, right? Don't put 500 here. Put the mass here. Right. So it's a typical mistake in the multiple choices. They will take that in account. So your acceleration is not as bad. If you get something larger than 10, that means you have done a mistake because you cannot, like free fall will be the maximum acceleration when you are going down. So if you find something more than 10, you are in trouble. That's not right. Okay? Now, Hmm? So because mg is the weight, right? Okay. Mg is the weight, it's a force, it's a pull, and the mass, it's confusing, okay? Because we have the mass, which is inertia, and we have the weight, which is inertia times 10. It's confusing because actually this is not true. Actually, Newton gravity is just an approximation. And then Einstein came and says there is no such thing as the force of gravity. That's why it's confusing between 10 and the mass and then the weight. It's because space-time is being curved, right? And actually we are being pushed by space itself in 3D. So Newton's second law, in that case, gravity here doesn't make sense. It's confusing. That it's not you. It's because that was before Einstein. That's why. So anyway, then you have up equals down. So you have the normal force equals mg cosine. Okay? Up equals down. And you're going to learn that the kinetic friction depends on how hard you are pushing on the snow. Harder you are pushing, more friction you will get. So if you have friction, then it matters if it's an elephant going down slope or a dog on ski. Because elephant will push harder on the snow, so it will have more friction so much that it won't slide. If you have a dog, it will slide. Okay, so the kinetic friction depends actually on the normal force. In that case, so the friction depends how hard the surface is being pushed. If you push really hard, you're going to have more friction. And it depends also on the material. Is it snow? Is it ice? Is it cement? Isn't that beautiful? It makes sense. Okay. Okay, so now I'm going to give you tricks to solve those kinds of problems. I call that the imaginary bag, and I put a copyright. Just because it's my idea. Okay, so I already show you how to solve those kinds of problems. It's going to be on the pop quiz, obviously, probably on the test. It depends what is your system. Okay, so you have to decide what is it that you're going to put in a bag. And if you use that way, those type of problems become very easy. So this type of problem looks scary. Now let's do this one first. It's less scary. And I'll show you my way to do it. If you understand, some people don't understand the way. Some people understand. But I will also show you the long way. Yep, different people have different glasses, it doesn't matter. So let's say it's accelerating. So here you have an acceleration A, and here you have the acceleration A. So first of all, conceptual question. This one is accelerating down, this one is accelerating up. Do you agree? This one has a large mass. So if the acceleration is down, that means, so you have two forces acting on this one, right? What are the forces? The weight and the tension, the rope. Very good, right? You all agree with that? Which one is the winner? Because the acceleration is down. The weight is the winner. So the first thing, conceptual question, you want to make sure the weight is down and the tension will be a little bit smaller. This is the winner. And then because the force is transmitted all the way, that's going to be the same tension here. but the weight is smaller. Very good. Okay, it's not that intuitive. The weight has to be smaller because the winner is this one because you're accelerating up. Okay. Now I show you my way to do it, and then I will show you the textbook way. Okay, so be careful. It's copyrighted. So what I do, I say, okay, let's make everything happens like all the system here is inside the bag. Okay, so this is inside the bag, this is inside the bag. So what is the winner? What makes the things goes down? The weight of the big one. Okay, so that will be mg. So that's the driver. Which one is the loser that make things slower? M. Very, very good, little m. Now, what's the inertia? Like the things, the mass. It has to be the total mass, right? Makes sense? Inside the bag, you're gonna have the big M and the small m times A. So if you do it that way, you go fast. Now, you don't have to do it that way. You can do it in 2 steps. So if I do it in 2 steps, I have to erase my bag. So the idea is always driver minus, you always, when you have 2 keys, there is always one lagging behind. So the same thing. Right? Okay. If you focus on this one, only on that system, are you with me? Which one is the driver now? Tension, very good. Minus the loser equals MA. Do you agree? And then you focus on this one. In that case, which one is the winner? Very good. Minus the loser, T, equals MA. So you have 2 equations with 2 unknown, 1 and 2. And if you add 1 and 2, the T goes away. So we're going to have mg minus mg equals m, and you factor out, and you get the same thing. Okay, so you have the long way to do it, and you have the short way. So all those problems with a pulley, even with an inclined plane, you can use the imaginary bag, or you can do it the long way. Any question? Okay, we get to the hard stuff, the challenging stuff. I see eyes rolling. We go back to that on Tuesday, but I'm recording, so you can always go back to it. Okay. At what time is the pop quiz? Now? 10, 12? Huh? 12:03. Okay, I'm gonna open it now. If